Thank you for having me again. So I'm Soumya. I work as a machine learning engineer at Development Seed remotely from India. I've been with DevSeed for almost 3 years now, and before that, I used to lead AI startups in India. So today we are going to talk about Clay, which is an open foundational model of Earth. This was built by DevSeed earlier this year. So a bit about Clay. So Clay is a nonprofit, and they are basically building AI models that could help solve Earth observation data and tasks. They believe in open data, open source, and open for business. So everything that we did in Clay project is completely open. So Clay Foundation reached out to DevSeed early this year, and they wanted us to build the foundation, the core of the model. And we built an initial release in January this year, and Clay V1 came out in May. We are currently working on a V1.5. That's a little better than V1. That is probably going to release end of this month. The model is open. It's trained on 70 million chips across 7 different satellites. And when we say open, it's open for business as well. So it's the code is Apache 2.0 license, and the weights are open rail. You can go to madewithclay.org. They have a platform now with the Clay model as its backend that allows you to do a lot of like semantic search, classification, those types of tasks. And you can also check out the documentation on the Clay Foundation in the GitHub. I assume everyone here would know what a foundational model is, but I don't know, like I was not aware of what the audience would be like. So a 30-second introduction to foundational model. Foundational model has to be generic. It's generally trained with massive amount of data in self-supervised or semi-supervised manner. We figure out an auxiliary task for which we don't have to label our data and train it enough so that it understands semantics of the data. We then take it and use it for the downstream application that is of interest to us. So that's in a nutshell what a foundational model is. Now, what is a geo-foundational model, and what's unique about it? So general foundational models that we have out there, they are not geospatial in nature. There has to be certain characteristic that needs to be there or built in to a model for it to understand geospatial data. And as we understand, like geospatial data is not just RGB. There are different types of satellites. All of them have different types of sensors, and the number of sensors might go from 1 to a few hundreds, right? So we need to support that. It's not just optical imagery. We also have radar, we have LiDAR, and the other thought process around is like even street view imagery is geo in nature. So probably the foundational model should also support that in the future. In terms of time, your data points are not like single time steps. They are generally available as series in time. So you need to have that into consideration. And those series are not continuous as videos, right? Like they're fairly intermittent with missing pixels, cloud cover that you can't really use in your model. And again, different satellites have different resolution. So Maxar has 30 centimeter compared to MODIS, which is like 500 meters. So there's a range of resolutions of the satellite. Along with all of this, like there is metadata that is generally there. So where on Earth that particular image is captured, when was it captured, what the weather condition was like, all those things also need to go into the model. So these were like some thought that we had initially when we were thinking about what a geo-foundational model would look like. And the other thought was, doesn't matter what satellite, what sensor, what time step, it's representing a unique feature on Earth, right? Let's say we are looking at a paddy field. Now, SAR satellite will look at it differently compared to Planet, compared to MODIS. But the feature that is represented, that is unique, and that is to be represented as unique, as a single semantically meaning thing in all the satellites, right? So the embedding for them in the model should be similar. So that was like our thought process on like, if we have to build a geo-foundational model, what it would look like. And these are some of the points that we came to think about. Having thought about this, the first step was like creating a data pipeline, given that you are building a large model, you would need a data pipeline that's efficient enough and that's representative of all the sensors of the entire world, not like biased to any particular geography or any particular satellite or any particular sensors. In terms of sampling, we use different types of sampling techniques for different types of satellites. So for Sentinel-2, 1, and Landsat, we did a global sampling. We used ESA's world cover, land use land cover data, and MGRS tile as our baselines. So for each MGRS tile, we computed land use land cover statistics, and then we clustered all of these together based on the LULC stats. Once we have created the clusters, then we randomly sample points from each of those clusters. We made sure that we oversample in regions that have a higher human footprint. For instance, like regions that have more urban characteristics or regions that have more agricultural characteristics. From our initial observation, like these were regions that had more entropy in the data, like they had more features from which the model could learn from. So it was uniformly sampled across the entire world, but a bit of oversampling was done based on some criteria that we thought would impact the model performance or give it more information to learn. For NIP, because this was available only in US, we didn't use land use land cover stats, but we used the points of interest dataset from Natural Earth. So for each point of interest, we took that particular tile, and we also like randomly sampled 1/3 of the tiles from the entire US. For lens, it was a bit tricky because we didn't have a stack catalog for lens, but the data was like segregated based on geography and the time that particular satellite was used to capture. Lens also had like varied resolution, going from like 15 centimeter to 1 meter. So based on that, we sampled from all of that. For Clay V1.5, we have also added MODIS, and MODIS is like uniformly sampled across the entire world like multiple times. Like I said, like because the model is big, the training is so big, your data process has to be efficient. So for V1.5 training, we had to like process around 5,000 chips per second, and each chip might have like bands from 2 to 10. So it's a lot of data. Initially, we thought like we will build a scalable pipeline that would pull the data from the web using Stack and Cobb and feed it to the model on the fly. But that didn't work for us because there was a data bottleneck. There is IO latency that is generally involved, and doesn't matter how efficient you handle your data pipeline, the IO bottleneck will always be there, and you're not overclocking your GPU, so that didn't work for us. So we use Stack and Cobb, the similar pipeline, to query for our data, pre-process, pre-download all of them, create chips, and then create cubes out of them. So initially we started with like single chips, but then if you're reading, let's say 5,000 chips per second, there's a lot of like CPU bound tasks and IO bound tasks that kind of slow down the data processing. So what we did is we shuffled the data and we created data cubes. So each chip has like 128 samples. So you load like entire cube at a time, and you do an internal shuffle of the cube, and then you shuffle in between cubes as well. So you have like enough randomness in your data between your epochs. Also make sure like your data pipeline is efficient for training the model. To store these things, we pre-process and store them in AWS S3. And we're using FSX Lustre Store from AWS that kind of links to your S3 storage and pre-pulls your data even before your model needs it. So that was like a good mix to build a good data pipeline. To do all of this, we wrote a library called StackChip. It's open as well. Now, we didn't use this StackChip for training, but it was used for pre-computing and creating the data cubes. But you can use StackChip for inferencing workloads. Let's say you want to generate embeddings for any foundational model for entire Portugal, right? So you could just pass the bounding box of Portugal along with the chip size that you want to stack chip, and it would then go and create the data cubes for you and save it, which you can then pass it through your foundational model and get your embeddings, which you can use for downstream task. Altogether, we had like 70 million chips and around 50 terabytes of data. These are like some of the statistics of how many chips we had for all the different satellites: Neptune, Sentinel-2, Landsat, C12-1, C12-2, and Sentinel-RTC. Modus is missing because I didn't get a chance to add it to the slide. Now this visualization is an indicative of like what the chips look like. I don't know if you can imagine this, but this is a representation of all the 70 million chips. And this was done using a LON board, again, like a visualization library that's built by a colleague of ours at FCED. So each point in here represents like one chip, and the color represents a particular type of satellite. So zooming in further, you can see like each dot in here basically represents a chip. So green, I think, is Sentinel-2, pink is Landsat, the blue dots in the back are NEP, and the purple ones at the bottom are Lens. I'll take a pause here if people have any question, or we can answer it later if you want, and I can move on to the modeling section. Is everything good? Like, is the pace okay? Cool. Okay, I'm assuming there's no question right now, but if there is, we can. Okay, so there's a question like, what's a chip? A chip is like the smallest data element that goes into your model. So it's like a 256 times 256 size Sentinel chip that has 10 bands. That's a chip, and the chip would change for your satellite. So there are tiles. So tiles are like the larger scenes that you get in stack catalogs, and then you break it into smaller chips so that you can feed it to a model. Now moving to the model side of things. Okay, sorry. So Clay is not a unique architecture, right? We don't have a paper of Clay because we didn't do a lot of R&D to build Clay. So what we did is actually we did a thorough literature review on everything that existed in terms of geo-foundational models. So everything that's there in Clay is something that we learned from any of the papers that had come at that time. So I'd like to give like all the credits to papers like Prithvi, Dofa, SatME, ScaleME, GeoFM, from where we basically picked the pieces that we thought were like super interesting and made sense to build something that's truly global and geospatial in nature. So it has dynamic embedding block that allows us to support multi-band imagery and multiple sensors. We use SAM as a teacher that acts like a North Pole for the model to make sure that it always understands basic feature. Doesn't matter what the satellite, what the time, what the weather condition. We use dynamical positional encoding and also ground sampling distance that is fed into the model. We also feed in location and time information to the model. The training is done using mask image modeling technique, or MAE. And then we also use Matryoshka's embedding. So you can take embeddings of Clay, which is of dimension 768, with Clay V1024, with Clay V1.5. And you could pick just the first embedding, or the first 10 embedding, or the first 20 embedding, and they would have enough information to help you with similarity search or classification. So it's stored under the MRL scheme. I'm not sure if you guys are familiar with MRL, but we can discuss it later if you want to. The model is 500 million parameters in size. It's trained on 70 million chips of size 256 times 256 times how many ever channels that particular satellite has. We use 75% masking for the chips, and we mask in space, we mask in channel, time, and lat long. It supports 7 different satellites right now, but from the testing that we have done, it basically understands data ranging from 30 centimeter to 500 meters or anything in between. So when I say this, Clay has never seen planet as an imagery source, but you can feed in planet and it can do classification, semantic search, segmentation on planet as easy as it does for all the other satellites that's trained with. It can take input of chips that are of any size. So any size that's a multiple of 8. So you can like feed in chips of size 32 to chips of size 1024. You can go further as well, but then like because we're using transformers, your attention computation increases. So you might like get out of memory. If you can fix it, like you can like pass in any chip size. Yep. Yes, Kelsey, I see you have a question.
Yeah, just quick question. So you talked a little bit about it being able to accommodate different spatial resolutions, but what about like hyperspectral data? Would that require like a new model, or is it something that you can incorporate into something like this? Or kind of what would the considerations be in terms of like compute power?
That's a great point. We did consider like feeding in hyperspectral data as well. And the way we have configured Clay, it's not too difficult. So you can take Clay today and there's a config file which allows you to add any data source. You just need to pass in like how many channels there are and what's the wavelength of the channels. Like that's kind of an indication of what data the model is seeing. And if you fine tune it for a few epochs, it will understand that data as well. So yeah, that, like to answer your question, yeah, it's possible to add that to the model as well.
And it's not it's not too, I mean, if we're talking about something like, 250 bands and hyperspectral image, like that's not too...
yeah, I don't see that as a challenge. Okay. No, cool. No.
Thanks.
Moving on. So yeah, this is the architecture of Clay. And this is the old architecture. The new architecture has changed slight bit, which I was trying to add to the slide just before our call, but then I couldn't. So I'll update it and put it in the drives that Biplav has shared. But it's more or less the same. So you have a dynamic embedding block that takes your sensor and how many bands it has. It takes the image and it splits it into tokens. Because we use 75% masking, we remove 75% of the tokens, take 25%, pass it through the Clay encoder, get its embedding vector. We pass the embedding vector through the decoder. The decoder again reconstruct the input image space, and you do a reconstruction loss. This is very similar to any other MAE model that you see. So any other model is trained using MAE like Prithvi or SATMAE, ScaleMAE, any paper, like they have something very similar. The other part to this is like there's also a teacher. So like I said, like Sam is a teacher. They also use Dino and other such teacher as well. So the tokens also go through the teacher and generate an embedding. And the new thing about Clay v1.5 is like you have Matryoshkas. So you take an embedding, you use Matryoshka to match it with the embedding of the teacher. So the representation learning is using MRL, the Matryoshka's learning, and the reconstruction learning is your traditional MI. Along with this, you also like feed in the ground sampling distance and the position information. So the ground sampling distance is convoluted with the position of the tokens. And then we also pass in lat long and time through the positional encoding as well. So everything, like all the meta information that you have there for your data, that kind of like is fed into the model. And the model learns it using two different types of losses. One is the reconstruction loss, the other is the representation loss. So after training, like how do you evaluate what your model has learned and how does it look like? So this is like a simple example. So you are seeing the image on the left. It's basically a beach, which has some sand, some water, and some structures in between. And each number here represents one vector in the embedding space. So you have, let's say, 768 vectors. Each number is a vector. So you take that vector and you try to visualize it for that image. Each vector tries to capture something unique about that particular image, right? So if you look at the vector number 97, you can see it's basically a segregator. It's a segmenter. You never train the model to do segmentation, but that's a property that the model has learned. If you look at number 102, you can see like that detects like sand that's underwater, right? So each vector. Some are visible to humans and some are easily interpretable for us, while others are like more convoluted and something that the model understands better and we don't, right? But each vector represents some unique properties of the image. You can take that and apply it across a lot of images. So here, like the first rows are the images, and the second rows are, you take one vector. I think we picked vector number 97 because it is doing segmentation really well. So you can see like we didn't train the model in segmentation, but it is clearly like able to like just segment information from the images out of the box. You don't have to do anything. Similarly, you can pick any other embedding vector and visualize what feature, what property it is able to capture and better represent in the images. In terms of training, because this was too big a model and too big a data set, we had to train it on a 20 node cluster. Each node had 8 GPUs. These are G6 series GPUs in AWS. So all in, we have like 160 GPUs spread across 20 nodes. We're using FSx cluster store as our data store, and it is of size 100 terabytes. To orchestrate this, we rely on AWS parallel cluster that basically sets up the clusters and creates the master-slave architecture for us. We store our preprocessed data in S3, attach the FSx store to it that pulls the data from S3, and then we use Learn to schedule our workloads across the entire cluster. Right now, it's taking around 7.5 hours per epoch, but each epoch is equivalent to two epochs, like the way we have written our data loaders and samplers. So it's around 4 hours an epoch, and an epoch has like 70 million chips that goes through the data, that goes through the model for one pass. And that's massive, right? And because this was like 500 million parameter model, it was able to like fit itself in one GPU. So we implemented DDP, and we didn't have to go for FSDP because DDP worked for us. Now we'll look at like few downstream tasks that we have tried with Clay, and all of these are on Clay V1, not on 1.5, because 1.5 is still training. It's in the last stages, so we have not yet done evaluation on that. But that's presumably much better than V1 with better support for sensors. So the first one was similarity search. What we did is we took the embedding vectors for an event, a pre-fire and a post-fire event for the Claremont fire. So you take the embedding vector, pre-fire and post-fire, and you take the difference of that, right? So that difference is basically your wildfire vector. You then search for the wildfire vector for the entire US. So the blue chips that you see are what was detected by the model as presence of wildfire that happened, and the orange ones are from the ground truth data that we had with us. Another simple example, this is also taken from the Clay doc. So you can just pick any region of interest where there's a particular feature that is of interest to you, maybe flood, maybe wildfire, maybe solar panels, or urban growth, whatever, right? And you could use stack shape to query for that query data for that area, pass it through the model, and do a PCA plot of it. And then the PCA by itself like clusters it based on what data it is. So here you can see each image is a dot, and you can see the two green ones at the top are like cloudy pixels. If you want to detect cloudiness in images, you could just like filter it based on that. The blue ones are like normal images, like images taken after that. And the red ones indicate like a wildfire event that happened and everything changed after that. We also like fine-tuned Clay on some downstream tasks. So we did semantic segmentation for Chesapeake Bay data. And this is like a variant of Chesapeake Bay, which has like 7 classes. So we subsampled 2,000 chips from Chesapeake Bay, trained Clay. Like when I say fine-tune, we don't touch the encoder. We just attach like a head on top of it for segmentation, and we just fine-tune the segmentation layer. So it was trained on 10 for 10 minutes for 10 epochs, and we could get a F1 score of 0.93 or IU of 0.875. But the other interesting thing is if you look at the loss curve, like the learning happens in the first or the second epoch. After first or second epoch, the model has already learned and it's pretty good at segmentation. So if you see in the visualization as well, the first one is the image, the second is actual, the third row is the predictions. You can see like after 10 epoch, the model has already learned a lot of the features, able to do it pretty nicely. So after first two epoch, the model is pretty good. After that, it tries to over optimize things. In terms of like the code, it's basically like it can fit in a single screen. You take the Clay encoder. Here you see the segment encoder from Clay. You extract intermediate features from the encoder, upsample them to the size of your segmentation mask. You fuse the features together and then do a segmentation. Like it's a very basic architecture, and yeah, with that you're able to get these scores. We also like tested it on a regression task. This is not like a traditional regression task, but this is like per pixel regression. So there was a Biomasters challenge that was hosted on driven data that had I think Sentinel-2 and Sentinel-1 data, and they were trying to estimate above ground biomass from this. So we only took like 5% of the data, and we only took like Sentinel-2, not Sentinel-1, and trained it for 20 epochs. And again here, like after the first 2 or 3 epochs, like the model was already giving us a score of like 0.35, and then after a few epochs, it gave a score of 0.30. If you look at the challenge that was hosted, like I think the winning solution was around 0.275 or 0.28. So yeah, you don't need to over optimize things, but if you are willing to spend 10 minutes on a small subsample of data with a foundational model, you can do a lot. Again, the visualizations are more or less like representative of the ground truth. The first rows are the images, the second rows are the actuals, and the third rows are the predictions. And this is like the I think the above ground biomass estimates from the images. We also tried it on classification on Eurosat dataset. We tried it for 2 minutes, accuracy of 0.985 in 2 minutes. But the point being, like, you don't really need to train it for like 50 epochs or 100 epochs, so you don't need a lot of data to solve a task. If you have access to foundational model, they can like solve your problem with 80 to 90% of what you can do with like doing a proper training in just 1 or 2 epochs. And then, yeah, you easily reach a point where the model is useful and usable. There is also a Clay application that the Clay team has built. DevState has not been part of the Clay app, but I'd like to like show that to the audience as well. So you can go to explore.madewithclay.org, and there you can like start searching for regions that is of interest to you. We tried, I think, adding text to Clay in between, and there is a very nice little project, but it is not really good. So we stopped it. We did Clay v1.1, v1.5, but we'll be also adding support for Clay in the future. So stay tuned on that. Right now, you can like do search on images. So you can browse through the Explore platform and select a feature. So here we are interested in football fields, and these are the American football fields. So you can select, I want to find all football fields in US. And then the model then searches and returns you some results. Now, not everything would be good because it's not representative. Like there'll be other things in the surrounding that the model also captures. But you can spend like in 5 minutes, you can have like a very good classification model. So you look at the initial result, you say, okay, this is what I want, this is not what I want. And then we do some embedding arithmetic on the backside and do a better search next time. And after 2 or 3 iterations, you have like a model that's detecting all the football fields that is of interest to you. Yeah, and then in terms of the team, so we have Lily, me, Viji, Leo, and Daniel who worked on this. It was like one of those projects where like the entire team, the pod at the seed that came together and built it. So like a lot of the heavy lifting was done by the team. So all thanks to them. That's all. Thank you. Yeah, you can like mail me, or you can open issues on Clay if you want to do something with it. You can reach out to us over email. Over we're also trying to figure out if we should have a discourse channel or something where people can come and ask questions and stuff. But the ask I think from Clay right now is for people to start using it or come up with use cases that we can help support you or like fine tune it for your use case. One last thought is like benchmarking, Clay. So this is something that a lot of people have asked, and unfortunately, we didn't have a lot of time to do like proper benchmark, but we'd like to do. We'd want to do something that covers the entire globe, right? Like a benchmarking data set that's robust enough, that's indicative of that geography of Earth, that's indicative of all the sensors that we interact with, and that's indicative of all the different types of problem that we'd like to solve using a foundational model. There are a few ones that have recently come. I think I was looking at Pangea dataset that came, I think this week. We'd probably want to support that, but if someone is interested to benchmark as well, feel free to like reach out to us. We can help you with setting up a cluster where you can benchmark and try out the model. So happy to help support that. I'd like to extend that as well. Yeah, so that's all. Like that's most of the presentation. I guess yeah, we can do a Q&A if people have any questions. There are a few questions in the chat which I missed. I'd probably like to answer that. So Aditya asked, are the chips raw or are they masked for clouds? Oh, that's a great question. So the chips are raw, but we do use some kind of filtering, but we don't remove all the clouds, right? Because cloud is like nature. It's supposed to be there in geospatial imagery, so you can't just remove it. Because if you train a model with cloudless, then if model sees clouds in the future, then those are alien things to the model, so you can't completely remove it. The filtering that we apply is like when we are selecting tiles, we only pick tiles that have, I think, less than 70% cloud cover, so that we have like good amount of entropy in the data that we can train for. And after we have selected those tiles, when we chip it, at that stage also we do some kind of filtering to I don't remember the exact number, but we do some kind of filtering to remove cloudy images. But we don't remove all of them. We remove like some of them and have enough so that the model has understanding of clouds during training. Okay, the other question is from Ate. Do you have examples using Clay for change detection? No, we'd love to do that. For change detection and for object detection, we don't have examples on the Clay repo yet. But after v1.5 release, we'll spend some time adding more examples, and I believe we'll add one for change detection as well. Then Aditya is asking, okay. Do you have estimates of reconstruction loss across space and time? We do log the representation and reconstruction loss. So yes, per chip we compute it, but I think you mean something different. Aditya, if you can ask it, like I'm not completely sure on this question. In the predictive sense, like overall, like how it does reconstruction, like we have not like tested it like by geography or by time, but from what we see, it does like pixel perfect reconstruction. Like with 25% of the data is able to like completely reconstruct stuff. But then there are these ideas where, let's say you take an image where, let's say there's a small hut in there, but you mask that hut out and pass it through the model. Can it reconstruct that hut? Like these are examples that we have not tested, but these are some of the ideas that are floating in the Slack threads that we'd like to test. Yep. Yeah, I think like those were the questions in the chat. yeah, I'm happy to, like, we have 5 more minutes, so happy to answer any of the questions.
Yeah, I'll start. Thanks, Soumya. That was really a good presentation and learned quite a bit. So you talked about when Kelsey was asking, like, it could take any number of bands and then any chip size given it's a multiple of 8. Maybe it's a dumb question, but can you explain what's going on within the clay model itself, that it's flexible enough to take, any number of bands or any number of chip size? Because like I've experimented with segment anything, and it takes like 3 bands, right? You could trick it in taking NIR or whatever other spatial bands within the remote sensing image, but if you give it like 4 bands, then it just will fail out. And then I see you're using Sam as a teacher in this clay model. So can you explain a little bit on the inner working on what's going on behind the scene?
Sure, yeah. That I try to explain. I'll try to explain that, right? Like, so there are two things, right? There's generally two restrictions to what you can feed into a model. One is like how many bands the input needs to have, and what's the size of it, right? Now, size is an easy problem. The reason you are restricted with size is because we use static positional encoders, right? Like, you know what input size you are supposed to receive, and based on that you create like your positional encoding beforehand, and that's why like you generally get error when you pass in a different size. But that's not required given that you are not dynamically generating the positional encodings, like they're pre-computed. You can just like generate it after you know what your chip size is. That's how it supports dynamic chip sizes. So any number that's a multiple of 8, because the path size is 8. So the smallest token is of 8 by 8. After that, any number it can handle, right? So that's on the size of the image. Now, in terms of the number of bands, that innovation actually comes from the DOFA paper. So they have introduced this concept of like a dynamic encoder. What it does, like if you like I think they have their own analogy on how it works. Like they relate it with how humans look at things and perceive and stuff. But my understanding and the way we have implemented it is like, so you basically want your input space, doesn't matter like what your input is, right? Like you project it into a space, a lower dimensional space, and then feed it to your model, right? So you just need to know what your input space is going to be. That's why like input to clay is a sensor. If it's a Sentinel 2, we know that it will have 10 bands. If it's a NIP, we know it will have 4 bands. Let's say you want to feed hyperspectral imagery that has 100 bands, right? So you need to pass that information to the model that I'm passing an input that has 100 bands. So the dynamic embedding block will take this information and then reproject it into a low dimensional space that is a unique channel times height time grid, which can then be used by the patch embedding layer to split and pass. This is something that I have seen like a Persever IO use as well. The Flamingo papers, like where they basically want to build stuff that is agnostic of what the input space looks like. The general technique is you take something that's unknown dimension and create a lower dimensional version of it, and then patch it and feed it to the model. I don't know if I did a good job at it, but that's how it does, like the image size and the number of bands.
Yeah, that makes sense.
And the way SAM works is because we don't pass all the bands through SAM, because SAM acts like a North Star, and we only compute like 5% of the loss in the representation, while 95% of the loss comes from reconstruction, right? So SAM only takes the RGB channels. And for, let's say, for Sentinel-1, you don't have 3 channels, right? So you need to mock a 3rd channel to be fed into SAM to reconstruct and stuff. Yeah.
Okay, yeah. It's kind of similar to dimensionality reduction sort of concept,
Yeah,
is it?
Dynamically reducing the dimensions, yes.
Okay, yeah, that makes sense. Thank you. Any other questions?
We'll have a minute.
Yeah. Maybe last question from myself. Have you seen any operational use case around this? I know you showed like a lot of example, but have people been using it operationally, so they keep refining the model with the newer data sets coming in?
We have tried a few use cases with some of the clients that use Clay, but that's built by the Clay team itself. So I would not say like something that someone has taken and done it, but there is like enough examples out there that people have built. I know someone tried to do earthquake detection using SAR data on Clay. Someone tried to detect like ice sheets on PlanetScope imagery, and that worked great. Some researcher from FDL were using Clay to segment, forgot what they were trying to segment. They're trying to segment something using SAR, and they're basically comparing across different foundational models, and Clay kind of gave like the best results there. So yeah, we don't, we have not benchmarked Clay, so it's not a claim we can do, but it works in most of the cases.
Okay. Yeah, I kind of feel like the wildfire tracking, monitoring those use cases probably can use some of the Clay model.
Yep.
Okay, I think, yeah, we're about time. Thank you so much, Soumya, for the great presentation. Once you have the slide uploaded, I'll put the recording and the slide on the channel. And yeah, thank you so much. And we hope you continue to join our working group and be part of it.
Sure, yeah, thank you so much for having me. I'll upload the slide now. I hope that it was a good use of your time today, but yeah, I'd love to like join back sometime.
Awesome. Thanks, everyone. We'll see you in 2 weeks.
Thank you.
Bye-bye.
Excellent. Thank you so much.